Hi, I'm Angela Rasmussen from the University of Utah Department of Electrical and Computer Engineering, and I'm going to be working on problem 2, which will be an inductor, so an RL problem where we've done mostly RCs up to this point. I'll refer you to the video about the steps to determine how to find the values for RL or RC circuits, and so I'm just going to skip right to the solution. So our first step is going to be to solve for the initial circuit. So we redraw the circuit and we leave out the element and we leave out the switch. And so this is going to be at time 0 minus, so an initial time. And in this one, we are trying to find IL of t. And so because of that, we're not going to have to take the extra step after this initial one. So right before the switch moves at 0 minus, what is the switch doing? You look at it and it's up or down. So in this case, it will still be up, so you leave it open. And then an inductor that sat there a long time becomes a short. So that will be a wire. And then we're going to solve this circuit for IL of t. So hopefully you can see here that if there's no source over in this portion of the circuit, and so IL in this case will be 0. But if you don't see that, you can put a node at the top of this, an unknown node, so I could label it Vx, and determine my ground, which will be there, and then I can do node voltage. It would be Vx minus 0 over 3.6k plus Vx over minus 0 over 7.2k. And then combining those, I get Vx and this number, and then I divide that number, or 0, by that number, and I'm still going to be left with 0. So if Vx is 0, IL has to also be 0. So that's mathematically how I could find that that was 0 if I didn't see that already. Okay, so that value, if I was trying to find some other variable in the circuit, I would then redraw the circuit and replace this with the current source of whatever value I found. And in this case, sorry, I drew the current going the wrong way. So you draw the current going the same direction that you found it in the previous solution. So that would be going down still, and then 0 amps. And so then I could then solve that. I would put the wire or the switch location at right after it's been switched. So it would be closed in this case. And then I can determine any other value or variable within the circuit. This would be the step where I would find the initial value for it. All right, so in this case, IL of 0 minus is going to equal IL of 0 plus, so our initial value is going to still be the 0. So that's our initial value. For our final value is, again, redraw the circuit, leave out the element, leave out the switch, and then determine the position. Going back to the original one, you see that after 0, it's moved, and then it sits there for a really long time. So it's going to be in the straight position. And then the inductor again sat there for a long time, so it's going to again be a wire. So now I'm going to determine IL from this, and I'm going to go back to that node voltage. So I label the top one Vx, and then I have minus 2.4 milli plus Vx over 1.2k is going to be this branch. And the first one was going opposite, going out. So I did the minus 2.4 milli because it's coming in. And then this one is Vx over 3.6k. And then this one, which is IL, is Vx over 7.2k. So once I find Vx, and then I can either use an online calculator, or I can combine all of these to have a common denominator. And then I can solve for Vx and divide it by whatever this number is. And 2.4 milli, I mean, over that number. And then Vx, I can get this value for Vx. So 1 over 1.2k. Or I can find a common denominator on this one, but this I think would be easier just to put that into my calculator. And then IL in this case is going to just be Vx over 7.2k. And that ends up being 4 over 15 milliamps. And this will be my final value, is 4 over 15 milliamps. My last step is tau. And in tau, I'm going to redraw the circuit again, leave out element, leave out switch. And then I'm going to put it in the final position for the switch, which in this case was down. And then I put A, B location on this. So, and then I'm going to remove the independent sources. When a current source equals 0, it becomes an open. So that means I'm basically going to ignore that branch. It's going to become floating wires. And I can draw it quickly so you could see if I was to open that up, it just becomes 2 floating wires. So my pathway now comes in from A, and then it splits and goes in 2 different pathways. So those 2 pathways will be in parallel to each other. And so 1.2k in parallel with 3.6k. And then those 2 pathways join again and go through the 7.2k to get to B. So it's going to be a plus 7.2k. So this then becomes 1.2k times 3.6k over 1.2k plus 3.6k plus the 7.2k. And then this yields an RTH of 8.1k. And then a tau is going to be L over RTH. And L was given as 81 millihenry. And so we're going to use 81 millihenry. So 81 milli over 8.1k. And that ends up giving, oh, I didn't calculate that one, but whatever that value is. The final value for IL of T then is going to be the final value, which was 4 over 15 milliamps, plus the initial, which was 0, minus the final, which is 4/15 milli, e to the minus t over this 81 milli over 8.1k. And that will be in amps. And then you can again write for t greater than 0, or you can just write u of t multiplied by this portion. So that would be the answer to this second problem. Thanks for watching.